Hello, my name is Bobby Pesch, and I am an undergraduate researcher working under Dr. Stephen Ralph at the Georgia Institute of Technology. Today, I will be discussing the work that I presented at the EPICA Industry Advisory Board meeting in May of 2023. EPICA is a National Science Foundation Industry University Cooperative Research Center. Through this program, students and industry experts conduct cutting-edge research that will enable the next wave of communications and sensing technologies for a wide variety of platforms by designing electronic photonic ICs and systems geared specifically for aerospace applications and harsh environments. As part of this mission, I, along with my fellow researchers, Arjun Khurana, Joel Slabby, and Jacob Heisner, under the advisory of Dr. Ralph, have investigated our team's current pipeline for designing photonic devices in an attempt to improve our overall design process. Our current process, density-based topology optimization, is a locally optimizing inverse design paradigm that continuously varies the geometry of a structure by computing the gradient of a given figure of merit with respect to all design parameters. Additionally, structures designed by this method may contain features that are physically non-intuitive, may have little functionality, or may violate DRC constraints required for fabrication. To develop an understanding of non-intuitive and commonly occurring features in TO designs, we performed 3 case studies on devices with notable TO features. Essential and non-essential features were identified and selectively removed. The variations in performance were then simulated. We first considered a broadband mirror, which featured periodic Bragg-like contours to the back side of the device. By removing these outer contours, we reduced the effective area of the device, which is needed for high-density integration. After this, new devices were optimized using smaller initial design areas, yielding better performance than expected in a smaller footprint. The second case study was an asymmetric 6733 splitter that featured 4 small outer islands. After simulation, it was evident that these contours were simply artifacts of the inverse design, yielding an average variation of only 0.58% in transmission across all modified designs. Finally, our last case study investigated a modal multiplexer, which featured both silicon and polysilicon layers, in addition to large interior holes and outer islands. We analyzed this structure by removing each feature type independently and then simulating the transmission of each mode. Investigation revealed that the interior holes were critical to the mode-splitting functionality of the device, while the outer islands may reduce crosstalk, and the polysilicon layer was primarily a source of loss. It was through this case study that we realized that within all TO designs, there is an identifiable set of features that are required to satisfy the original figure of merit. Through these case studies, our intuition for the utility of recurring TO features has greatly improved, leading us to propose a novel modification to the existing pipeline. After our conventional TO is performed, we will now remove any extraneous artifacts from the device, leaving only the functional topology. Next, shape optimization will be employed to maximize performance. In this step, we have the freedom to seed the shape optimization with either existing functional topologies or other physics-informed designs, while also specifying a new figure of merit. This flexibility in the figure of merit will allow for existing designs to be repurposed for any arbitrary use case, such as a new frequency band or splitting ratio. In the future, we seek to first employ the proposed paradigm by improving several existing structures, namely the modal multiplexer. We also plan to validate the technique by repurposing existing designs for a new application. That concludes my discussion. Thank you for listening.